Hello, in this video I want to talk about the null space and row space are orthogonal complements. And this video is basically about what that even means. So before we get into the theory, let's just look at some examples. So let's say you have this matrix A, this 2 by 2 matrix, where the first row is 1, 2, and the second row is 3, 6. Now what's the row space? Let's figure out what the row space and null space of this matrix are. So the row space of A is the span of the rows. Well, I have these two rows, 1, 2, and 3, 6, right? So the row space of A is the span of 1, 2, and 3, 6. Well, notice that 3, 6 is just 3 times the vector 1, 2. So here's the vector 1, 2, and here's the vector 3, 6, and then the row space of A is all the vectors on this line along that vector. So that's the row space of A. It's one-dimensional. It's this line that's spanned by 1, 2. Okay. What about the null space of A? So for the null space of A, remember what that means is all the solutions to AX equals 0. So we have to solve AX equals 0. And when you set up the augmented matrix, AX equals 0, what happens is you're going to get a row of zeros on the bottom. And so now we have to write out the equations. We get x plus 2y is equal to 0. And we see that x is a leading variable and y is a free variable. So we set y equal to some parameter, and then we get, so x is negative 2y, so x is negative 2t. And so the vector xy is any multiple of negative 2, 1, right? We get that from here. And so the solutions to AX equals 0 is the span of negative 2, 1. So the null space of A is the span of negative 2, 1. Okay, so where's negative 2, 1 here? So I labeled the vector here 1, 2, and then negative 2, 1. Let's put that in a different color. So negative 2, 1 is like here. So negative 2, 1. Now notice, so this is the null space of A, this line. So notice that this vector, negative 2, 1, is orthogonal to 1, 2, because this is negative 2 times 1 plus 1 times 2, which is 0. Okay, so the null space and row space of this particular matrix A, they're both lines, and they're perpendicular lines. Now, if you think about why that's true, it kind of makes sense, because if you have a vector in the null space, A times x has to be the 0 vector, right? So if the vector x1, x2 is 0, 0, if this is in the null space of A, then you know that the dot product of 1, 2, and x1 has to be 0, and the dot product of 3, 6, and x1, x2 has to be 0. So that gives you some clue that, yes, if you have a vector in the null space, it's going to be orthogonal to the rows of A. And it turns out that if you're orthogonal to the rows of A, you're going to be orthogonal to every vector in the row space of A. So every linear combination of the rows. Okay, let's look at a different example. So let's look at a 3 by 3 matrix. So let's say that A is this matrix. The first row is 1, 0, 0. The second row is 1, 1, 0. And then the third row is 2, 1, 0. Okay. What's the row space and null space of this matrix? Well, again, the row space is just the span of the rows by definition. So it's the span of 1, 0, 0, 1, 1, 0, and 2, 1, 0. Now, are these three vectors linearly independent or dependent? They're linearly dependent. In fact, this third vector is the sum of the first two. So it's 1, 0, 0, the first vector, plus 1, 1, 0. So we can remove it from our set that we're going to span, and then the span doesn't change, right? Because this vector was a linear combination of these two, and so the row space of A is really the span of 1, 0, 0 and 1, 1, 0. Now these two vectors are not parallel to each other, and so they're linearly independent. And so the row space of A is this plane that's spanned by these two vectors. Actually, what do you think this plane looks like? So here's R3, x-axis, y-axis, z-axis. What do you think? Let me draw this for negative. What do you think the row space of A, which plane is this row space? Well, if you look at there's kind of a clue, which is to look at the third components. They're both 0, right? So the z value of these vectors is 0. So these vectors are on the xy plane. So 1, 1, 0, 0 looks like this. It's here. That's 1, 0, 0. And then the second vector, 1, 1, 0, is like this. And together they span the xy plane. So all the vectors on the xy plane, that's the row space of A. Okay, so in this example, the row space of A is the xy plane. Now what about the null space? Well, again, for the null space, we're going to have to solve Ax equals 0. So let's figure out what the null space is. So A is this matrix, and we're solving Ax equals 0. And when you row reduce, you might want to pause the video and check that this is what you get. You get this. Okay. Yep. Okay. So now we have to solve. Well, this is easy because the first equation is just x equals 0, and then the second equation is just y equals 0, right? This first row reads as 1 times x equals 0. The second equation is y equals 0, and you have a 0 row. So that doesn't tell you anything, but you have this free column. You have a free, this third column is free, and so z is a free variable, and so you said z equal to t, some parameter, and so therefore the vector xyz, any vector in the null space is going to be t times the vector 0, 0, 1. Because remember, this x is equal to 0, in particular 0t, y is 0 times t, right? And z is 1 times t. Okay, so the null space is all multiples of 0, 0, 1. So the null space of A is the span of the vector 0, 0, 1. And that is, so here's 0, 0, 1. That's the z-axis. So the null, well, 0, 0, 1's here. But the null space is the span of that single vector. That's the z-axis. So that's the null space of A. And notice again that you see this pattern that the null space of A is perpendicular, right? This z-axis makes a 90-degree angle with the xy plane. Okay, let's take one more example. So let's say that A is this matrix. By the way, just to go back to this example, I want to emphasize, because sometimes students, when they get here, they're not sure what to do with this column. But remember that any variable is either a leading variable or a free variable. So in this matrix, you either have a free column or a pivot column. So this column doesn't have a pivot, so it must be a free column. So z is a free variable. Okay, I just wanted to clarify that. Okay, let's go on to the next example. The last example. So let's say that A is this matrix. Okay, clearly I designed this matrix so that the second and third rows are linear combinations of the first row. So I see that the row space of A is the span of just the first row. I mean, it's the span of all three rows, but since the second and third rows are parallel to the first row, you can just write that it's the span of the first row. So the row space is a line, and it's spanned by this vector. Okay, let's draw the picture here. So 0, 1, 2 is something like this, or maybe here. Okay, so the span of this vector, that's the row space of A. Now, what's the null space of this? So in the previous example, the row space of A was a plane, and the null space was a line. Well, we actually know what the null space, what kind of shape it will be because of the rank and nullity theorem, right? The dimension of the row space plus the dimension of the null space must be the number of columns. So since A has 3 columns and the row space is one-dimensional, you know that the null space is two-dimensional, so it's a plane. It's a plane for the origin. Now, which plane for the origin? Well, to say which plane for the origin it is, we have to actually solve Ax equals 0. So let's solve Ax equals 0. Sometimes I write NUL of A, but instead of N of A, but it's the same thing. It's the null space of A. It's just that some books write R of A for the range of A, which is a different thing. So that would actually be the column space instead of the row space. So, I usually will write R of A, but when I write R of A, it means the row space, but other people will mean it to mean something else. Okay, so the null space of this matrix. So we solve Ax equals 0, and then when you row reduce, you get this. And now what are the free variables? Well, we have one leading variable, which is y, and then we have two free variables, which are x and z. So x is free, x and z are free, and y is not free. So let's say x is equal to t, and we set z equal to s. Then this equation reads y, the first equation is y plus 2z equals 0. So y is equal to negative 2z. So then we can write that x, y, z is equal to, so let's just set it up, a column for t and a column for s, and x is equal to t, so you have a 1 here, and then y and z are both in terms of s, so it's 0, 0, and then for s, x is equal to 1t plus 0s, and then y is equal to negative 2s, and then z is equal to s. So the null space of A is the span of 1, 0, 0 and 0, negative 2, 1. And where is that in our picture? Well, notice that this vector 0, 1, 2, let's look at that vector that spans the row space, and then these two vectors that span the null space. And you'll notice that if you take the dot product of these vectors, so if you take 0, 1, 2 dotted with 1, 0, 0, you get 0. And if you dot 0, 1, 2 with 0, negative 2, 1, you also get 0. And that matches what we suspected from the previous examples, that the vectors in the row space are orthogonal to the vectors in the null space. So what the null space is going to look like if you draw an accurate picture is it's going to be the plane that's orthogonal to this line. Okay, so it needs to make a 90-degree angle, so it's going to be something like this. So this is going to be, your vectors 1, 0, 0 are going to be on this plane that's orthogonal to this line. So 1, 0, 0 is somewhere there, and then 0, negative 2, 1 is like here. Here. Okay, maybe this isn't the most accurate picture, but it's supposed to make, this vector 0, 1, 2 is supposed to make a 90-degree angle with the vectors on the plane. Okay. It's basically supposed to be like this. Okay, I just didn't draw the picture super accurately, so maybe it doesn't look like the line is perpendicular to the plane, but this line is supposed to be sticking straight out of this plane. Okay. And these examples illustrate, if you go back to all the examples we did, in this first example, the null space and row space are perpendicular to each other. They form a 90-degree angle. Here, the row space and null space are lines, and the dimensions match up, right? The null space is one-dimensional, the row space is one-dimensional, 1 plus 1 is 2. 2 is the number of columns. And in the next example, you have the same scenario. You have a 3 by 3 matrix. The null space is one-dimensional, the row space is two-dimensional, and the null space is spanned by the line it's spanned by the vector that sticks straight out of the row space. It's a normal vector to the plane, if you're used to this terminology of normal vectors. And in this third example, you have the same scenario. Oh, I should probably label this as the null space of A. The row space of A is the line that sticks straight out. It's orthogonal to the plane, which is the null space of A. So these these examples all illustrate this theorem, which is that if A is any matrix, so let A be any matrix, any m by n matrix. And the examples I did, the matrices were all square, but they don't have to be square. The theorem says that the set of vectors orthogonal to every vector in the null space of A is precisely the row space of A. Okay, let's read that sentence carefully to make sure we understand what it's saying. So it's actually saying two things. The first thing it's saying is that if you have a vector that's orthogonal to every vector in the null space of A, it must be in the row space of A. Okay, that's thing one this is saying. And then thing two this sentence is saying is that conversely, if you have a vector in the row space of A, it's orthogonal to every vector in the null space of A. Okay. And then the second thing is, well, yeah, this is the main theorem. This is the theorem. So when you have something like this, we say that the row space of A and the null space of A are orthogonal complements. And what we write is, so the set of vectors orthogonal to every vector in A, the notation for that is you write n of A and then this perpendicular sign to the top and right. That's called the orthogonal complement to the null space of A. So, and then the row space of A, of course, is just the row space of A. So then the theorem says that this orthogonal complement to the null space of A is equal to the row space of A. I'll do it in purple just to make it match. Okay. We can actually think about why this is true. Let's prove this statement. So first of all, let's say that you have a vector that's orthogonal actually, I'm going to prove a slightly different statement. So I'm going to prove this other statement, which is that the set of vectors orthogonal to every vector in the row space of A is the null space of A. So this is saying that if you take, so the set of vectors orthogonal to every vector in the row space of A, that's the orthogonal complement of the row space of A is the null space of A. So null space of A. Okay. This one is actually the one that we'll prove. So we'll prove this sentence. So let's put a star next to it. So let's prove star. So again, the sentence is saying two things. It's saying that, so the first thing is, suppose that V is orthogonal to the row space of A. the statement says that V is in the null space of A. Well, if V is orthogonal, so orthogonal to the row space of A means orthogonal to every vector in the row space of A. Well, if V is orthogonal to every vector in the row space of A, then it must be orthogonal to the rows of A, because the rows of A are in the row space of A. So V is orthogonal to all the rows of A. Well, if you have a matrix, okay, let's say you have this matrix A. Okay, it's going to have some rows. So you have the first row, the second row, all the way to the mth row, right? So if you have a vector, okay, that's orthogonal to each of these rows, that means that you get 0 when you take A times V. And so therefore, V is an element in the null space of A, because A times V is the 0 vector. That's what it means to be in the null space of A. Right, so here we're using we're thinking of matrix multiplication in terms of the dot product. The row space, so the first row of A times this vector is the first component, and so on. Okay, then the second thing we have to show is suppose that V is in the null space of A. If you're in the null space of A, well, that means that A times V is 0. A times V is the 0 vector, so V must be orthogonal to the rows of A. Now, can you see why, if you have a vector that's orthogonal to every row in A, why do you have to be orthogonal to every vector in the row space of A? It's because of the property of the dot product, right? If you take a linear combination, so every vector in the row space of A so let's call this vector x, is a linear combination of the rows of A. So let's say that x is C1 times the first row of A plus C2 times the second row of A, and so on up to Cm times the mth row of A. Well, what happens when you do V dot x? This is, you can distribute, so, okay, I'll show the steps. So it's V dot this thing, okay, which I'll write out. So C1 times row 1 of A plus dot 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 plus Cm, the scalar, times row m of A. And then you can distribute the dot product, so you get it's V times C1, so C1 to Cm are scalars, row 1 of A plus dot 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 plus V dot Cm, row m of A. And then you can pull these Ci's are constants, so we can just move them out. So this is C1 times V dot row 1 of A plus dot 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 plus Cm times V dot row m of A. And since V is orthogonal to the rows of A, each of these dot products are 0. So you just get C1 times 0, which is 0. So you just get 0. You're adding 0 a bunch of times, and so you get 0. So therefore, since V dot x, right, V dot x we show is 0, that shows that V is orthogonal to any vector in the row space of A. So it must be orthogonal to every vector in the row space of A, because X was an arbitrary vector in the row space of A. Okay? So that's the proof of that statement. The statement that the set of vectors orthogonal to every vector in R of A is equal to the null space of A. It actually doesn't easily follow. This first statement that I said is true, that the orthogonal complement of the null space of A is the row space of A, but it doesn't actually follow immediately from the statement that we just proved. You can prove one direction, that if you're in the row space of A, it has to be orthogonal to every vector in the null space of A, but the only part that is not clear is how do you know that if you have a vector that's orthogonal to every vector in the null space of A, how do you know that it must be a linear combination of the rows of A? That's the part that requires a bit more theory than I'll explain in this video. Okay, so now that we know that the row space and null space are orthogonal complements of each other, let's look at a consequence of this. So this is the end of the proof. That's the symbol to mean the end of the proof. Okay, let's look at a consequence of this theorem. So we know that the orthogonal complement of the row space of A is the null space of A. Okay. And this is true for any matrix A. So since this is true for any matrix A, well, what that means in particular is that if you start off with the matrix A and you take the transpose, that's another matrix, right? So it must hold for A transpose. So what does that tell us? So the row space of A transpose, the orthogonal complement of that is equal to the null space of A transpose. Okay. Now let's make it clear that this is saying the orthogonal complement to this row space of A transpose, right? The row space of A transpose is this subspace, and the orthogonal complement is equal to the null space of A transpose. So these two subspaces are the same. Well, what's the row space of A transpose? What's another word for that? If you take A and you take the rows of A, then you get the row space when you look at the span. But if you take A and then transpose it, those rows of the transpose were the columns of A, because taking the transpose swaps the rows and columns. So this is actually, i.e., the row space of A transpose is the column space of A. So the orthogonal complement of the column space of A is equal to the null space of the transpose of A. And we'll actually use this fact. This fact will be useful when we talk about least squares solutions. When we learn about least squares solutions. Okay. And if you want to practice this, it might be a good idea. It would be a good idea to just look at the A's, the three A's that we did, and then just like I found the row space and null space of each of these and showed that they're orthogonal to each other, do the same thing for the column space and the null space of A transpose. That would be a good practice. Okay, so what did we do in this video? We looked at some examples of the null space and row space of matrices, and then we saw the pattern that, you know, they're not just random configurations. Like if the null space is a plane, okay, and this is in R3, then the row space is the line that's orthogonal to the plane. And similarly, if the row space of A is a plane, the null space is the line that's orthogonal to that plane. That's if A is a 3x3 matrix. And then in the 2x2 case, if the null space is a line, then the row space is a line. Actually, this even holds for invertible matrices also. If you have an invertible matrix A, then the null space is just the zero subspace, right? It's just the set consisting of the zero vector, and the row space is Rn. And also, if the kind of on the flip side, if A is just a matrix that's all zeros, then the null space of A is Rn. It's every vector A times that vector is a zero vector if A is a zero matrix, and then the row space will be the span of the rows. But if the matrix A is just all zeros, then the row space of A is just a zero vector, right? It's the subspace just consisting of the zero vector. So it really is true for any matrix. And it's also, in these examples, I did square matrices, but it's also true for any m by n matrix. It doesn't have to be a square matrix. And then we proved, so there's actually two parts to this theorem. We proved only one part of the theorem, but it's this part that will actually be useful when we talk about least square solutions. All right, thanks for watching.